In this video, I will explain Opamp stable multivibrator concept. Opamp stable multivibrator concept. A stable multivibrator is a free-running oscillator having two quasi-stable states. This one is a stable multivibrator using Opamp. Multivibrator using Opamp. It is used to generate square wave, A stable multivibrator is a free-running oscillator having two quasi-stable states. Having two quasi-stable states means plus V set and minus V set. These two are virtual states of the stable multivibrator. There is a oscillations between these two states. Oscillations means plus V set at one level, plus V set at another time, minus V set. That means there is oscillations between these two states and no external signal are required to produce the change in state. There is no triggering signal required. There is no external triggering signals are required to produce the change in state. It is free-running oscillator which switches continuously between its two unstable states. Next, Opamp is operated in a saturation range. Saturation region. Opamp is operated in saturation region. Opamp is operated in saturation region. Saturation region. That means the output of the Opamp is either plus V set or minus V set. It is a free-running oscillator circuits continuously switches between two states, either plus V set or minus V set. The principle of generation of square wave output is to force an op-amp to operate in the saturation region. The principle of generation of square wave output is to force an op-amp to operate in the saturation region. A stable multivibrator circuit is a circuit that has no stable states. It means once power on, it starts and it continuously to oscillates between high and low states until the power is off. High means plus V set, low means minus V set. A stable multivibrator circuit, a stable multivibrator circuit is a circuit that has no that has no stable states. That has no stable states. It means once power is on, it starts and it continuously oscillates between high, that means plus V set, and low, minus V set. Oscillates between high and low states, that means plus V set and minus V set, until the power is off. Until the power is off. A stable multivibrator is a free running oscillator. A stable multivibrator, stable multivibrator is a free running oscillator having two quasi stable states, having two quasi stable states. Quasi means not permanent. It continuously switches between the states. It has no stable states. It means once power is on, it starts and it continuously oscillates between high, that means plus V set, and low, minus V sets, until the power is off. That is called as quasi. The oscillations between these two states, there is an oscillation between these two states, and no external signals are required to produce the change in state. Continuously oscillates between these two states only. There is oscillations. There is oscillations between these. There is oscillations between these two states, and no external signals are required to produce the change in state. Stable multivibrator using Opamp. It is a free running oscillator circuit. It is used to generate square waveform without any input signal. It is continuously oscillates between two states. The two states are nothing but either plus V set or minus V set. It does not require any external signal to change the state of the stable multivibrator. It continuously, it is a free running oscillator. It continuously oscillates between two states. It has two quasi-stable states. Quasi means it continuously virtual states. Virtual states continuously at one time. It looks like say, the stable multivibrator is at plus V set. At another time, it looks like minus V set, like that. Next one, circuit diagram. Another important point is this is the circuit diagram. Later we'll explain. A stable oscillator circuit that generates a square wave output using an RC timing network connected to the inverting input of the operational amplifier and a voltage divider connected to the non-inverting input of the op-amp. A stable oscillator circuit, a stable oscillator circuit that generates a square wave the square wave output using RC RNC timing network circuit or network connected to the inverting input of op-amp, inverting input of the op-amp. Inverting input of the op-amp and a voltage divider and a voltage divider connected to the non-inverting input of the op-amp. Non-inverting input of op-amp. That means this is the op-amp used in a stable multivibrator circuit. Here's some timing circuit. Timing circuit consists of R and C elements. Timing circuit consists of R elements connected to inverting input of the op-amp and voltage divider voltage divider circuit. Voltage divider circuit. Voltage divider circuit is connected to non-inverting terminal of the op-amp. With the help of these two, generates a square wave. Maintain two states. That means plus V set and minus V set. These are some important points related to op-amp stable multivibrator circuit. Next one, circuit diagram. This one is op-amp minus plus inverting terminal and a non-inverting terminal. Timing circuit is connected to inverting terminal of the op-amp. That means here capacitor is here. Capacitor. The voltage across this capacitor is VC. And some resistance, feedback resistance. R is connected here. This one is R. And the second one is a voltage divider circuit. A voltage divider circuit. That means here this one is R2. R1 connected to non-inverting terminal of the op amp. This is the voltage divider circuit. Voltage divider circuit. This one is a combination of R and C is the combination of R and C is the timing circuit. Timing circuit. Here output voltage, here output V0 across load resistance RL. Here there is no input signal is applied to this circuit. It generates square waveform. It generates square waveform like that. Maintains at two states, plus V set and minus V set. Now we will see how to generate the square waveform. Here the voltage at non-inverting terminal of the op amp is V reference. V reference. Next one is a fraction of beta. That means R1 by R1 plus R2 of the output is fed back to the positive input terminal. A fraction of the output is fed back to the fed back to the positive input terminals. Positive input terminal. That is beta is equal to this is the fraction of output R1 by R1 plus R2. A fraction of not input, a fraction of the output is fed back to the non-inverting terminal. That means plus input terminal. That is equal to B is equal to R1. Beta is equal to R1 plus R1 by R1 plus R2. Here the reference voltage is equal to V reference is equal to total voltage applied to the circuit is V0 into R1 by R1 plus R2. That is equal to V0 beta. Beta V0. Beta V0. This is the reference voltage. Vc is the capacitor voltage. The open loop gain of the op amp is AOL. With the help of that positive feedback only, any circuit generates oscillations. The positive feedback is provided with the help of this voltage divider circuit. Consists of R1 and R2 elements. A fraction of output is connected to positive terminal of the op amp. That means non-inverting terminal of the op amp with the help of R1 R2 voltage divider circuit. VID, here two voltages are there. Here in that stable multivibrator, op amp is used here. The operation of the op amp is analogous to comparator circuit. Comparator means compare two voltages at inverting terminal of the op amp and non-inverting terminal of the op amp produces an output voltage. We know that V0 is equal to gain into VID. Gain into VID. Gain is AOL. VID means difference between these two voltages. One is V reference, another one is VC. V reference is connected positive terminal of the op amp. VC is connected to negative terminal of the op amp. Therefore, VID is equal to V reference minus VC. V reference minus VC. We know that the op amp is in saturation mode. That means here saturation means like that. Characteristic curve is like that. plus V set minus V set. The output is switches between these two states, V naught. This one is delta VID. Delta VID. Based on that sign of this difference voltage, output V naught is obtained. That is either plus V set or minus V set. Based on this sign of the VID, difference voltage. Now operation. This one is an op-amp. Capacitor C connected to inverting terminal of the op-amp. Some resistance R is here. Some voltage divider circuit consists of R1 and R2 is connected to non-inverting terminal of the op-amp. This one is R2. This one is V0. For simplicity purpose, okay, RL is also connected here. This one is V0. This one is VC. This one is V reference. V reference is equal to V reference is equal to V0 into R1 by R1 plus R2. Therefore, V0 is the V0 into beta. Suppose V0 is plus V set, V0 is at plus V set. V reference is equal to beta V set. V0 is equal to minus V set, suppose, because the op-amp is at stable multivibrator has two quasi-stable states. It has two unstable states. Unstable means continuously oscillates between these two states. V reference is equal to minus beta V set. Okay, first case one. Initially, case one. Initially, the voltage across the capacitor is 0. VC is equal to 0. VC is equal to 0. Whenever that power is switched on, in the op-amp multivibrator circuit, the op-amp works as an equivalent comparator circuit. It acts as comparator circuit. Comparator means compare the two voltages, VC and V reference. Comparator circuit. Once power is switched on, once power is switched on, V0 is equal to V total output offset voltage, V over T. V0 is equal to V over T. Therefore, V reference is equal, initially VC is equal to 0. Initially VC is equal to 0. V reference is equal to beta into V over T. Output is generally V reference is equal to beta V0. V reference is equal to beta times V0. Here V0 is V over T, total output offset voltage. Difference voltage is equal to VID is equal to V reference voltage minus VC voltage. VC is 0. V reference is beta times V over T. VC is 0. Therefore, the difference voltage VID is equal to beta output offset voltage. This is positive. This one is positive. Output voltage of the op amp V naught is equal to gain into, that means AOL, VID. AOL into VID. Therefore, V naught is equal to AOL times, practical case it values 2 into 10 power 5 for 741 IC. VID is beta into VOT. The difference signal is here, VOT means V reference is greater than VC. That means VC is 0. Therefore, output is maintained at positive. V naught is positive. V naught is positive means, according to characteristic curve, the output is V set. V naught is positive means here VID is positive. VID is equal to, we know that VID is equal to V reference minus VC. V reference is equal to beta times V over T. That is positive. That means positive set. Therefore, output voltage is plus V set. V naught is equal to plus V set. V naught is equal to plus V set. Therefore, represent in this figure, okay, V naught is maintained at plus V set. V naught is maintained at plus V set. Okay. Once V naught is at plus V set, this one is minus plus V naught is equal to plus V set. Some capacitor is there. Here capacitor C, not this one. Here connected here some resistance. Resistance is connected. Resistance is connected here. Resistance R is connected here. This is the voltage VC. Here the voltage is here. The voltage is V reference. V reference, that is beta VOT. Beta VOT. V reference voltage. Or beta output is output voltage is V set. Output voltage is V set. Sometimes it is also called as beta times V naught. VOT means V set. VOT means V set. Beta is equal to V reference is equal to beta into V naught. Once V naught is plus V set, the capacitor is continuously charges. The capacitor is charges towards V set. The capacitor charges continuously towards plus V set. Because here V naught is equal to plus V set, some resistance is also there. Some capacitor is connected like that. Therefore, the current I is obtained due to this V set. With the help of that current, the capacitor is charges towards plus V set. The capacitor charges towards plus V set. Here like that. This one is VC towards V set plus V set. Compare VC with V reference voltage. Compare VC with V reference voltage. Here V reference voltage is beta times V naught, but beta V set. Beta times V naught means beta V set. Here plus V set, beta V set is here some somewhere here. This is dash line like that. Initially, the capacitor voltage is 0. Vc is equal to 0. Here, Vc is equal to 0. Due to this condition, the capacitor is charged to 2 volts plus V set and reached to this reference voltage. This reference voltage, that means here at a time t1. At a time t1. Just it crosses, this is the VC voltage, crosses this V reference point. Suppose crosses these reference point, find out VID. Find out VID. VID is equal to VID is equal to V reference minus VC. V reference minus VC. At time t1 here, just reaches time capital T1. E is equal to capital T1. The capacitor voltage reaches to V reference. That means B plus B set. Once this capacitor voltage just crosses this V reference voltage, that means plus B set. Therefore, VC is greater than, just crosses means VC is greater than beta V set. VC is greater than beta V set. V reference is beta V set here. Beta V set. Okay. Therefore, output voltage, the difference voltage is negative because VC is higher value, V reference is the lower value. Here minus n, the difference voltage VID is negative. VID is negative means output voltage V0 is equal to AOL into VID. AOL into VID. Therefore, this one is negative. VID is negative. VID is negative means VID is negative means in this action, the output voltage V0 is at minus V set. The output voltage is at minus V set. The output voltage is at minus V set. Therefore, at T greater than T1, that T is greater than capital T1, the capacitor voltage just crosses the V reference voltage. That means plus B beta saturation, B saturation. Therefore, output of the stable multivibrator is switches to another state, that is plus V set to minus V set. Plus V set to minus V set. Plus V set to minus V set. Here plus V set to minus V set. This one is V reference is also changes. V reference is also changes. That means V minus plus V0 is equal to minus V set. V reference voltage here. V reference voltage is equal to beta V0. That is equal to V0 is minus V set. Minus beta V set. Here the capacitor voltage here is VC. The capacitor voltage is VC. This is the capacitor. This one is a resistor R. The resistor R. Now V reference voltage is equal to minus beta V set. Beta at T greater than T at T is equal to T1. The capacitor voltage VC is equal to beta V set, beta V set, beta V set. T greater than capital T1, VC just crosses this V reference voltage. Therefore, that is the difference is negative. It is analogous to the op amp is analogous to comparator. Compare these two voltages, VC and V reference. Therefore, V naught is equal to minus V set. V naught is equal to minus V set. When the voltage at the negative input terminals becomes just greater than the reference voltage, the output is driven into minus V set. As long as the capacitor voltage VC is less than V reference, the capacitor voltage VC is less than V reference. That means plus beta V saturation. The output voltage remains at plus V set. The output voltage is remains at plus V set. When VC in this region, VC is less than plus beta V set, the output voltage maintains at plus V saturation. At this instant, the voltage on the capacitor is beta V set. The voltage at the capacitor is beta V set. It begins to discharge through R, that is charged towards minus V set. Here, the capacitor voltage here is beta V set. Beta V set. At the time t is equal to T1. Once capacitor is discharged, V naught is changed to minus V set, switches to another state. The capacitor starts discharge. At this instant, the voltage on the capacitor is plus beta V set. It begins to discharge through R, that is charged towards minus V set. That is charged towards minus V set. That means here, discharging means here, towards minus V set. One more level is also introduced here, that is V reference, negative reference voltage here. Negative V reference. That means minus beta V set. Minus beta V set. This one is like that. When the output voltage switches to minus V set, the capacitor charges more and more negatively until its voltage just exceeds minus beta V set. Important point here is just suppose this capacitor voltage, this is the VC, just crosses minus beta V set reference voltage. Now, okay. When the output voltage switches to minus V set, this one minus V set, here minus V set, the capacitor charges more and more negatively. Negatively means towards negative axis, below this time axis. That means negative axis, more and more negatively until its voltage just exceeds minus beta V set. This is the minus beta V set. Minus beta V set. Voltage just exceeds minus beta V set. Next, find out VID. VID is equal to VC minus V reference. V reference. That is equal to VC minus V reference is more wrongly mentioned here. VID is equal to V reference V reference minus VC. VC. V reference is minus beta V naught. Here VC is the capacitor charges more and more negative. More and more negative means VC is negative. Here negative into negative is positive. Therefore, minus beta V naught plus VC. Therefore, VC is greater than V reference. VC is greater than whenever VC is greater than V reference. Therefore, output voltage is equal to gain times V reference, VID. VID is positive, more positive. VID is more positive. Therefore, V naught is changes to plus V set. V naught is changes to plus V set. V naught is changes to plus V set here. Plus V set like that. Changes to plus V set. Therefore, the output of the stable multivibrator oscillates between these two states, plus V set and minus V set. Plus V set and minus V set. Repeated, same action is applied repeated here. Again, the capacitor charges and reach to this point. Once this point is reaches, the output of the stable multivibrator is switches to minus V set. The capacitor is discharges, reach to this point, just crosses minus beta V set, and again the capacitor switches to plus V set like that. In that fashion, the square wave is generated. The square wave is generated. Now, determination of time period. This is the waveform representation. The output voltage plus V set. P reference is equal to beta V set. This one is time period T. Minus V set. V reference is equal to minus beta V set. Like that. Already explained. Initially, the output voltage is plus V set. The capacitor is charges like that. Initially, VC is equal to 0. Once reached to this point, just crosses beta V set. It switch back to minus V set. Minus this one is T1. T is equal to T1. This point is capital T1. Once switches to minus V set, the capacitor is discharged more and more negatively and reaches to this point. Here, at that instant, the output of the stable multivibrator switches to plus V set. Plus V set. Again, the capacitor is charges and crosses to this, reach to this point, plus beta V set, and crosses this beta V set. The output of the stable multivibrator switches to minus V set. Minus V set. The capacitor is discharges like that. The frequency is determined by the time it takes the capacitor to charge from minus beta V set to plus beta V set, and beta V set to minus beta V set. Consider this for determination of frequency. Consider this portion. Consider this portion. The frequency is determined. The frequency is determined by the time it takes the capacitor to charge from minus beta V set to plus beta V set, and vice versa, Consider this portion, total time period, charging time period, and charging of the capacitor positively and the charging of the capacitor negatively. This one is positively, this one is negatively. Okay, the voltage across the capacitor as a function of time is given as the voltage across the capacitor as a function of time. Is given as, general formula is given as Vc of t is equal to Vf plus Vi minus Vf e power minus t by R into C, where Vf is called as steady state voltage, Va is called as input voltage. Steady state voltage and input voltage. Here steady state voltage is plus V set, Vf. Finally reached to this V set, but at middle some V reference voltage is there for comparison. Therefore Vf is plus V set, and V in is the capacitor voltage is starting from this point. V in is here minus beta V set. Therefore Vi is equal to input voltage, starting voltage. Vi is equal to minus beta V set. Vf is equal to plus V set. Substitute these two values in that above equation. Vc of t is equal to Vf is equal to plus V set minus Vi is equal to minus beta V set. Vf is plus Vs plus V set. That means minus V set e power minus t by Rc. At time t equal to t1, t1, that means the voltage across the capacitor is reached to plus beta V set. At a time t is equal to capital T1, Vc of t is equal to beta V set. Vc of t is equal to beta V set is equal to V set minus beta V set minus V set e power minus t by Rc. Here V set is cancelled. Therefore, beta is equal to 1 minus minus into minus plus. Here beta plus 1 e power minus t by Rc. Here beta minus 1 is equal to beta V sat is equal to V saturation minus 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 T by RC. V sat minus of minus V sat minus 1 plus beta. E power minus T by RC. Here minus into minus plus. This one is plus. This one is plus. Plus into minus minus. Okay. Clear. V set is cancelled. Therefore, beta is equal to 1 minus 1 plus beta e power. Here T1. Here T1. Capital T1. At T equal to capital T1 only, VC of T is equal to beta V set. T1 by RC. T1 by RC. This one is beta minus 1 minus 1 plus beta e power minus T1 by RC. E power minus T1 by RC is equal to 1 plus this one is 1 minus beta. This one is 1 minus beta by 1 plus beta. Change this one e power T by RC, T1 by RC. That means 1 plus beta by 1 minus beta. Apply natural logarithm here. Ln E T1 by RC is equal to ln 1 plus beta by 1 minus beta, that is equal to T1 by RC is equal to ln 1 plus beta by 1 minus beta. Therefore, T1 is equal to RC ln 1 plus beta by 1 minus beta. But time period is equal T is equal to, this one is T1, this one is T2. Total time period is T is equal to T1 plus T2. This is the symmetrical square wave form. T1 is equal to T2. Therefore, T1 plus T1. Therefore, T is equal to 2 T1. T is equal to 2 T1. Capital T is equal to 2 T1. That is equal to 2 into RC ln 1 plus beta by 1 minus beta. This is the time period. The square waveform f is equal to 1 by t. That is equal to f is equal to 1 by t 2 RC ln 1 plus beta by 1 minus beta. We know that beta is equal to fraction of output R1 by R1 plus R2. That is 1 by 2 RC ln 1 plus R1 by R1 plus R2 by 1 minus R1 by R1 plus R2. R1 is equal to R2. Suppose R1 is equal to R2. Therefore, F is equal to 1 by 2 RC ln 1 plus R1 is equal to R2 is equal to, that means 1 R1 by 2 R1, 1 minus R1 by 2 R1. that is equal to once f is equal to 1 by 2 RC, the beta value is here. One plus 1 by 2, 1 minus 1 by 2. 2 RC ln, that is 3 by 2 by 1 by 2. 2 to cancel, that is equal to 1 by 2 RC ln